Okay, here we are, 5-9, day 2. And we just covered the fundamental theorem of calculus, which is evaluating the integrals using the boundaries. And today we're going to look at some special cases of the definite integral. So special cases of definite integral. And remember, when we're doing an integral, the mathematics behind it is it's multiplying the x and y variables. Okay, you're multiplying y times x. Typically, we call that the area under the curve. We're going to see it may not quite be this. So, our first one. If I asked you to evaluate the integral from 1 to 4 of x squared minus 5x plus 2 dx, could you do that? And then we're going to look at that answer and why it's come up the way it is. Okay, first of all, again, when there's a 1 here, there is no inside. Just do each term separately. So, taking the antiderivative of x squared, we add 1 to the exponent, multiply by its reciprocal, add 1 to the exponent, multiply by its reciprocal times the 5, that'll give me 5 halves, plus 2x, and remember I don't need the plus c if I'm going to put in my boundaries because the c's just cancel out. So we're going to evaluate from 1 to 4. So it's always top boundary goes in first, minus bottom boundary. So, if I go use the table feature, I type in 1/3 x cubed minus 5 halves x squared plus 2x, and the table I want 4. So at 4, I get negative 10 2/3. If you look at the bottom, 0.6 repeating. So negative 10 2/3 minus, when I put the 1 in, I can scroll up to get that. Let's see, what fraction is that? Negative 0.1666. If you want the fraction for that, negative 0.166666, just fill the whole line up. Then go math frac, negative 1/6. So now to do the subtracting, this will be plus. So negative 10 plus a negative 2/3. I can just go negative 32/3. That's quicker. Negative 32/3 plus 1/6 is negative 10.5. Okay. Square units. So here I got an area that's supposed to be negative. Well, is area ever going to be negative? Not in our world. So let's see why this answer is coming up negative. So we got a negative integral, and we typically call that the area, but let's see why the integral is coming up negative. If I go back and look at the graph of this, let's see, don't want that. I want the actual originally function, x squared, the parabola, x squared minus 5x plus 2. It's a parabola, and if I look at it from 1 to 4, it's right down here. So this is what I've got. From 1 to 4, I'm finding this area right in here. Well, if you think about it, what an integral is doing is it's breaking this up into little tiny rectangles and multiplying the height times the width, because there's my y variable and my x variable is the width. The y is the height. So if you think about it, every y value is coming up negative because they're all below the x-axis. So on all of my rectangles, the height is negative, and my width, because I'm going 4 minus the 1 and dividing it up into all the pieces, that's positive. So anytime I multiply a negative times a positive, I'm going to get that negative answer. So in this respect, we say the integral is negative, but the area under the curve would be 10.5 square units. We wouldn't say a negative 10.5 square units. That doesn't make sense. So area is always positive, but the integral is negative. That's just showing us one of our dimensions was negative. Okay, let's try another one. Let's go from pi over 2 to 0. That's different than we've had of cosine x dx. Okay, so what has cosine as its derivative? Very easy, that's the sine. There's nothing to worry about on the angle. Derivative there is a 1, so it was good to go. And we evaluate from pi over 2 to 0. Top boundary first. So sine of 0 minus sine of pi over 2. So sine 0 is 0. Sine of pi divided by 2 is 1. I get negative 1 for my integral. Let's see why it's coming up negative. So I'm doing y cosine graph. Zoom trig. And I only want to look at it from pi over 2 to 0. So window, y min is 0, or x I mean, pi divided by 2. Now if we graph, all I'm looking at is that first hump on cosine. Maxes out at 1, crosses at pi over 2. Well, if we look, the graph is above the x-axis, so when I draw my little rectangles in here, which is what the integral is evaluating, my heights are all determined by points on this function, and all of these heights are positive. It's my widths that are different, because here I went 0 minus pi over 2. I took the smaller boundary and subtracted the larger boundary. That's going to give me my widths to be negative, which is why my integral is coming up negative, leading me to think I have a negative area. But again, integral is negative, area will be positive. Okay, there's 2. So here we had a negative height with a positive width. Here we have a positive height with a negative width. Now, example 3, evaluate the integral from 4 to 1. So again, there's that bigger to a smaller, so we'll be going smaller minus bigger. That should give us a negative width. My equation is negative 5 dx. Let's think about this one before we actually evaluate it. This is the line y equals negative 5. That's a horizontal line down at negative 5. So if I go down at negative 5, I've got a horizontal line. I'm evaluating from 4 to 1, 1 to 4. It's just a nice rectangular region here. But should our answer be coming up positive or negative when we calculate this? Well, let's think about it. Here's my little rectangles. My heights are all negative, and actually negative 5 because it's consistent all the way through there. So my heights are all equal to negative 5. My widths, because I'm going 1 minus 4, my widths are all going to be negative, which should give me a positive integral when I'm done. And when we're done, we should be getting, and we know the dimensions of this rectangle. It's a 5 high by 3 across. We should be getting 15. And we should come up positive 15, because anytime we come up with the negative times the negative, we're going to get positive. Well, let's see if we get it. So doing the integrating, that'll just integrate to negative 5x. evaluate from 4 to 1 or 1 to 4. So plugging in the 1, I get a negative 5. Subtract, putting in the 4, I get a negative 20. Negative 5 plus 20 is 15. So here we had an example where our heights were negative and our widths were negative, giving us a positive. Okay, next special case. I think we hit everything we can hit there. We're going to switch gears just a little bit. If I have the function, the quantity 2x plus 1 squared, and if I evaluate from 1 to 3, that same function, 3 to 5, and 1 to 5 of that same function. Okay, so take a look. I've got the same function in all three integrals. Here I'm evaluating from 1 to 3. This one's from 3 to 5. And this one is from 1 to 5. Do you think any kind of a relationship is going to exist between these three integrals? Think about that for a second. 1 to 3, 3 to 5, and 1 to 5, all of the same function. Well, hopefully you can see that it makes sense that if I added these two answers together, it should equal this one. Because this is essentially going from 1 to 5 when I put these two together, because they're connected at the same boundary there. So that's our conjecture, and we're going to work it out to see. All right, integrating this. I only have to integrate once because it's the same function. Because this is a 2 out here, we do have an inside. So the inside is 2x plus 1. The derivative of the inside is a 2. So that tells me I need a 2 next to the dx, which means I need a 1/2 out in front before I can do my power rule. So now applying the power rule, got the 1/2 times this to the 1 more power, and then times the reciprocal. So I get 1/6 times this quantity. Okay, we're going to evaluate it from 1 to 3, 3 to 5, and 1 to 5. So the 1 to 3, let's see, definitely going to use the table here. We came up with 1/6 quantity 2x plus 1 cubed. I want a 3. So the first one, when I plug in 3, I get 57 and 1/6 minus, putting in the 1, 4.5. The second one, I need the 5. That's 221.8. I got to figure out what that fraction is. 0.833333 repeating. So I'll quit. 0.8333333333. 56 minus the 3 was 4.5. And then the 5 was 221 and 5/6 minus the 1 was the 4.5. Oh, did I put this one in the wrong spot? I did. This was the 57.